Hey folks, and welcome to my narrow phase collision detection tutorial. We will be using a method that encompasses swept spheres. Before or while watching this video, it wouldn't hurt to read up on some of the math that will be involved, namely transformation matrices, dot products, cross products, basic trig functions, and general vector math like vector addition and normalization. And we'll also touch on planar equations as well. I'll be writing my code in Java using Eclipse, but the core concepts will hold in any object-oriented language, and I've written the code as procedurally as possible to make it the coding side of things easy to follow. That being said, there's quite a bit of optimization you can do, and I'll talk briefly about that as well. In addition to optimization, I'll give some quick information concerning broad phase collision detection, as well as collision response at the end. Before we get started, I'd like to give a brief overview of what exactly we're going to be doing in our code. So we've got this entity in the world that we're trying to model, and it's got some velocity vector associated with it. And hopefully there are some other objects in the world that we can collide with, such as a tree. Turns out that these other objects are made up of meshes of vertices, and these vertices are connected together to form triangles that we render onto the screen. Each of the triangles has 3 points with X, Y, and Z quantities associated with it for its world position. So what we're trying to do is detect a collision between the mesh of our object and the plane or edge or vertex of a triangle. But what we're going to do is approximate our mesh instead with an ellipsoid to make the calculations much easier. And further, we're going to be applying a transformation matrix to everything in our vector space, and we'll be transforming it into E-space, which will make the ellipsoid that surrounded our mesh actually a sphere, which will make the calculations much easier because, of course, the radius of a sphere is constant. And in fact, we'll be making ours a unit sphere, so the radius will always be 1. So yeah, quick recap on the entire process. First, we'll take in some world quantities from R3. These quantities are the world position, velocity, and the 3 points of the triangle we want to test for collision against. We'll then model our world positions as being the center of an ellipsoid. At this point, we'll transform all of the quantities to E-space with a matrix that has the inverse of the ellipsoid's maximas as its diagonal entries. And from here, we can calculate the sphere's distance from the plane. We'll then figure out at what time the sphere intersects with the triangle's plane by dividing the distance by the velocity. And if this time matches our program's next tick, then we can figure out if the intersection point is on the triangle's surface, edge, or vertex. Once we have this information, we're done. So enough talk, let's get into the program. So I'm going to start out by creating a new project, and hopefully you'll already have a project that you're working on, some sort of application that you want to detect your collision in. Next, I'll be adding some jar files into my build path, and they are from the legacy lightweight Java game library, and I will put a download link to those in the description of this video. They just contain classes for matrices and vectors. So if you want to follow me by rote, then I would recommend pausing the video and going and downloading these and adding them to your build path. The next thing we're going to do is create a new package, and this will contain the collision classes. We'll make a class. One of them will be the collision detector, and we'll code this second. We're going to make another class first, and we'll call this second class our collision packet. Now, the collision packet will just be an object that we can store collision values within. So we're going to need a vector that contains 3 floats, and we'll call it the collision position. We'll have a float for the collision distance, and we'll also have an integer for the type of collision, so we know if it's between a vertice or an edge or against the surface of the triangle. Next, we will generate a constructor for this class. So when we actually detect an object, we can create a collision, or rather when we detect a collision, we can create a collision packet and set the values to whatever we calculate. Next, we'll add some getters and setters so we can actually get those values and modify them. And I'll import the vector3f from the lightweight Java game library. And that is our collision packet class done. So we'll move into our collision detector. I'm just going to start out by declaring a bunch of objects that we will be using. So the first one is going to be a vector3f, and we'll call it the ellipsoid position IR because it is the position initial in real space. Next, we'll need an ellipsoid position, and that is the initial position in E space. And next, we will need a vector3f called the triangle P1R, and so that's the first point of our triangle in real space. And we're going to need 3 of those, so P2R and P3R. And we're going to need to have also those points in E space, so I'll declare 3 more of those vectors for those 3 triangle points in E space. And I'll import the vector3f. Next, we will need a few more vectors, and these are going to be edges between points, and we're using the points to construct vectors that are parallel to the plane of the triangle, and we will use these to calculate a normal vector to the plane. Next, we will need some more vectors, and these are going to represent the plane intersection point in both real space and E space. And so these are the points at which the sphere or ellipsoid actually intersects the plane. Next, we're going to need a vector, and this is for the plane normal I was talking about before that we'll get from those edges. And we will also need another vector for the plane unit normal. So that will just be the plane normal that's been normalized and has a magnitude of 1. Next, we will need 2 floats, and these are going to be the plane constant d and the plane constant p, and we'll use these in our calculations later. I'll describe them later. We'll need a float for the distance, and we'll need a float for times at which the sphere is intersecting the plane, so we'll call that t0 and t1, and we'll also need a vector3f for the velocity in real space, and of course we'll need one for the velocity in E space as well. Next, we will need a matrix 3f, and this will be our transformation matrix, and it will take things from our E space, or rather from real space to E space. And we'll also have another one of those transformation matrices that will take our vectors from E space to R space, or real space, R3. We'll also need a collision packet to represent the collisions that occur, and we'll have 3 of these, one for the vertex, one for the surface, and one for the edge. So those are the 3 types of collisions that are possible. Of course, there's also the null collision or no collision at all. So we now will need a constructor for our collision detector so we can actually use this within our game loop. And this is going to take in a vector3f position, vector3f velocity. We're going to need the points of the triangle, and so these are both vector3f's, P1, vector3f, P2, and P3. And we'll also need our ellipsoid's x maxima, the ellipsoid's y maxima, and also the ellipsoid's z maxima. And these are going to shape our transformation matrix. So inside, we will just quickly set our variables equal to the constructor's arguments. So this ellipsoid position IR is equal to position. This velocity r is equal to velocity. And actually in my version of this, I'm getting these values from the player, of course, rather than feeding them in. I would say that this ellipsoid position is equal to player.get position, or this velocity r is equal to player.get velocity. So continuing on, we need to set the points of the triangle to the triangle P1Rs. And we'll also set the main diagonals of our 3x3 matrix, our transformation matrix, to the inverse of the ellipsoid x maxima, the inverse of the ellipsoid y maxima, and the inverse of the ellipsoid z maxima, respectively. So those are the top left, the middle entry, and the bottom right entry. And yeah, so that's the constructor complete. So the next thing we're going to do is create a method that will just take our matrix, our transformation matrix, and multiply it by all of our real vectors and bring them into E space and store them in our variables. So we'll do that by calling matrix 3f.transform, and the left is the 2E space matrix. The right is the triangle P1R, and we'll save that in triangle P1E. We'll do that for each of the triangle's vertices, P2R, P2E, P3R, P3E. We'll also call that transform method on our real velocity and store that into our velocity E. And we're also going to take in our position. So that's our ellipsoid position IR, and we'll store that in ellipsoid position IE. So next, we will need a method that will construct some collision values for us. And we're going to start by drawing two vectors, u and v, and u is defined by p1 minus p2, and v is defined by p3 minus p2. And of course, these vectors lie within the triangle's plane. Now, we can calculate a normal vector to the plane by taking the cross product v cross u. At this point, we can look at the equation of the plane, ax plus by plus cz plus d is equal to 0, and note that it looks very similar to a dot product. And we know that the dot product of two orthogonal vectors is 0. So by taking the dot product of a normal vector and any vector that lies along the surface of the plane, then we can easily find out our coefficient d. And this coefficient d will allow us to find out another coefficient, p, and the coefficient p is used in a formula to calculate the signed distance of any point from the plane, which is incredibly useful to us. Because our sphere's radius is 1, anytime that we find a distance of 1 from our sphere's position, which is given by this formula, to the plane, then we know that a collision has occurred. And we can find the times when collisions will occur by substituting in that parameterized equation into the signed distance formula. And it will give us t0 and t1, which are the times that it collides with the front surface of the plane and the back surface of the plane. So there are three sets of solutions, three cases that we will deal with. The first of them occurs when the normal vector and the velocity is 0, and that will throw us some undefined times. And this is happening because the sphere is traveling parallel to the plane, so it will never intersect. So that makes complete sense. The second will be if the times are both outside of the range 0 and 1, and in this case, the sphere will not intersect the plane at any meaningful time. And then third, if we do get a time between 0 and 1, then we can use this as our intersection time and use it for our calculations. So let's get back into the code and write this all out. So I'll start by creating another method that we will call construct collision values, and it returns void. So first we're going to start by constructing those vectors between P2 and P1, and so this is a vector 3f, and we will subtract triangle P1E, and we'll subtract triangle P2E from that and store it in that P2 P1E vector. And then we'll do the same thing between points 2 and points 3. So vector 3f dot sub triangle P3, triangle P2E, P2, P3E. And it's very important that you get those in the correct order. So now we can calculate our plane normal by taking vector 3f dot cross P2, P3E, P2, P1E, and store it in that plane normal. And once again, it is very important you get the order of those correct, otherwise we'll be getting negative values. And then the plane unit normal is equal to vector 3f dot normalize, actually just plane normal dot normalize. And then we'll store that in the plane unit normal. And so that will return a vector that has the direction of the plane normal but a magnitude of 1. Next we will make those plane constants, plane constant d, and this is equal to the plane normal x times any triangle point, I'll use P2, triangle P2E dot x times -1. So I'm just going to be adding up all of these terms of this plane constant d that I showed the equation for earlier. So we'll need the plane normal y with the P2EY, and we'll also need the plane normal z with the triangle P2E dot z. And next we will be able to find our plane constant p, and this is equal to the plane constant d divided by the square root of the plane normal's x constant squared plus the plane normal's y constant squared plus the plane normal's z constant squared. So make sure that you get all of these parentheses correct. Y, z, z, semicolon. All right. Now from here we can calculate the distance. Oh, and I actually messed this up. That's our plane constant d there. So now we can calculate the distance at any time, which is going to be a vector 3f dot dot plane unit normal with the ellipsoid position IE plus the plane constant p. And that is our signed distance. So now we can find the times at which the distance is 1, and that will be t0, and we'll find the time at which the distance is -1, and that will be t1. So t0 is equal to 1 minus the distance divided by vector 3f dot dot, and it's the dot product of the plane unit normal with the velocity e. And then t1 is very similar, it's just -1 minus the distance divided by the exact same thing, vector 3f dot dot, plane unit normal, and the velocity e. So now we want to catch those different cases, and so we'll surround it with a try-catch, and we'll try to catch this illegal argument exception, call it E, and that will occur when the dot product of the plane unit normal and the velocity E is 0, because that's in the denominator. And we'll add that same try-catch to the T1 statement, and if that happens, we'll just say that T0 is equal to 0 and T1 is equal to 1. And we can't discard them yet because the sphere could actually be embedded in the plane, and so the collision would occur at all times, and so we'll have to test for that as well. And we also want to swap, make a simple swap method here to make sure that T0 is less than T1. So float temp is equal to T1, T1 is equal to T0, T0 is equal to temp. All right, and that is that method complete. So now we can move on to our actual detect collision method. And so this is going to return a collision packet. And yeah, let's jump into it. So first we'll start out by calling the methods that we wrote above, send values to eSpace and construct collision values. And then next we need to check if the sphere is traveling parallel to the plane. So we compare the dot product of the plane unit normal and the velocity vector to 0. And if that returns true, then the sphere is traveling parallel to the plane. And there are two possibilities. If the sphere is traveling parallel to the plane, if the distance is greater than 1, then there will be no collision ever. And if the distance is less than 1, then the sphere is embedded within the plane. And so it is always colliding with the plane. So I wrote out there, if the absolute value of the distance is greater than 1, then we can return null because there will be no collision. Else, if now we're catching if T0 and T1 are outside of the potential time ranges, the parameterization of T between 0 and 1, then we also want to return null. So if T0 is less than 0 or T0 is greater than 1, and then we also want to do that for the other side as well. So and T1 is less than 0 or T1 is greater than 1. And then if this returns true, then we can return null as well. But I actually have to get these parentheses correct. So now we know that the sphere will intersect with the triangle's plane at some point between T0 and T1, or 0 and 1, but we don't know if that intersection point is actually within the triangle. So next we need to calculate where that intersection takes place and also figure out if that's within the triangle. The equation for getting the plane intersection point is actually quite basic. It's merely the sphere position minus the plane normal plus T0 times the velocity. And hopefully you can see why that is from the diagrams below. So now implementing it in the code, we can write plane intersection point E is equal to a vector 3f subtraction between the ellipsoid position initial in E space minus the plane unit normal. And I'll cast that to a vector 3f. And we'll store that in the plane intersection point E. And then we also need to have that velocity times T0 in there as well. So I'll make a term for that, a new vector 3f, velocity E multiplied by T0, and that is going to be velocityE.scale, and we'll scale that by T0. I need to cast this to a vector 3f apparently. And now that I have these two quantities, we can calculate the true plane intersection point. So plane intersection point E is equal to plane intersection point vector 3f dot add plane intersection point E and the velocity E x t0, and we'll store that in plane intersection point E. So now we have to find out if that plane intersection point is actually within our triangle rather than just the triangle's plane. And there's a really nifty way to figure this out, and what we do is draw a vector from each of the points to the point that we're testing and normalize those vectors so they have a magnitude of 1. And then we take the dot product of each set of those, so dot product of P1, P2, dot product of P1, P3, and dot product of P2, P3, and we take the inverse cosine of that, and that gives us the angles in between. If all of those angles add up to 2 pi, then the intersection is within the triangle, and so we have a collision detected on the surface. So now jumping back into the code, let's make a new public method that's going to return a Boolean. We'll call it check position with triangle, and we need to take in a vector 3f, which is our position, a vector 3f, which is the triangle P1, another vector 3f. We'll just call that P1 for brevity's sake. Vector 3f P2, vector 3f P3, and that is all that we need for this method. So we'll start out with a float value that we will call angles, and we will set it to 0 at the beginning. We'll need a vector 3f, and we'll call it v1. It's a new vector 3f. Need to actually set that vector to something, so we'll subtract the position. We'll subtract p1 from that and set it into vector 1. And we're going to do that same thing for each of the triangle's points, creating vectors between them and the triangle or the intersection position. So P2 is sub position minus P2 stored in V2, and V3 will do the exact same thing, except we will say P3. Alright, so now we have all of the vectors that we are going to take the dot products between. So, but first we have to normalize them and make their magnitude 1. And then we'll simply just loop through all of these and increase our angles by the arc cosine of the dot product of, so for this one we'll do V1 and V2, and then we'll do the exact same thing again. We'll do it 2 more times, one between V3 and V1, and one between V3 and V2. And now our angles variable will hold the total sum of all of the angles between our 3 vectors, and so we just have to return a conditional statement basically checking to see if those angles add up to 2 pi. And I'll throw in a little leeway here, just in case there's some rounding errors. All right, and that is the check position with triangle method complete. So now we can actually call that method on our plane intersection point E. So we'll say if check position with triangle, and we'll feed into it the plane intersection point E. We'll need the triangle P1E. We will need also the triangle P2E, of course, and the triangle P3E. So now that will check those points, and if that returns true, then we have a collision with the surface, so we can create a new collision packet. Collision packet surface is equal to new collision packet, and we can return the collision position, which is equal to the plane intersection point E, and the collision distance, which is simply the sign distance, and the type, which is 0. And I actually commented that differently, but we're not going to return a null collision packet, so I'll use 0 for the surface collision. And else, if it doesn't collide with if the intersection point is not within the triangle, so that those angles didn't add up to 2 pi, then we still have to check to see if the sphere collides against edges or vertices. So we're going to do the same thing as before and parameterize the sphere position as a function of time. And we know that we'll have a collision with a vertex whenever the distance between those is 1. But we can actually square that. So the distance will still remain 1, but it will allow us to use the quadratic formula with these coefficients a, b, and c as our coefficients. And if you want to go into the math behind that, just go back and do the exact same thing as we did before, simplifying it, except use the distance between the positions squared. And of course, we're going to get 2 solutions from this because we'll get the positive solution and the negative solution, and we'll just take the smallest solution that's between 0 and 1, the smallest real solution that has a meaningful consequence to us. So we'll also have to take into account when the determinant is less than 0, because we don't want any imaginary solutions. And also, we have to check every vertex before we make any conclusions about which type of collision packet we want to send. So because we might check the first vertex and we might detect a collision, but that doesn't mean that the second or third vertex isn't actually closer to us, and we want to only detect the collision with the closest position. So we will do that first as well. All right, let's jump back into the code and actually write this all out. We are going to initialize a few objects. The first one will be a vector 3f, which is the ellipsoid vertex distance. And we are also going to need the opposite of that, which we will call the vertex ellipsoid distance rather. And we're going to need a float, which we will call the vertex time 1. We'll need a float for the vertex time 2. We'll need a float for the smallest solution vertex, which will be the final solution that gets passed or used in the calculations of the final solution. We need a vector 3f. We'll call it collision point. We need a float, and this will be a, and I'm just getting this calculation from the previous screen, so velocityE.lengthSquared. And we will now say that the ellipsoid vertex distance is equal to vector 3f subtraction ellipsoid position IE minus the triangle P1E. And we'll put that into the ellipsoid vertex distance. All right, next we need our float B. And so that is 2 times the vector 3f dot product of our velocity with the ellipsoid vertex distance. All right, and now we can calculate the vertex ellipsoid distance. Oh, spelled that one wrong. Vector 3f sub triangle P1R, oh no, that should be triangle P1E, ellipsoid position IR, vertex ellipsoid distance. Yeah, we'll change that back to P1E, and that's the ellipsoid position IE. All right, now we need to float C, which is equal to the vertex ellipsoid distance length squared minus 1. All right, and so now we need to see if the determinant is greater than 0, and if it is, we can continue on. So if 4AC is greater than or equal to 0, and actually I didn't catch this here, but it should be the square root, it's b squared minus 4AC, if that is greater than or equal to 0. And I'll catch that at the end. I'll go back and fix that. So vertex time 1 is equal to b squared plus double math square root 4AC, even though that's wrong, it should be b squared minus 4AC divided by 2a. And this is just the quadratic formula. And we will need to do this again for the vertex time 2, except just with a subtraction instead of the addition between the b term and the square root of the determinant. All right. So now if vertex time 1 is less than vertex time 2, so it is the smaller of the two solutions, and vertex time 2 is less than T1, see that should be vertex time 1, and vertex time 1 is greater than or equal to T0, and vertex time 1 is less than the smallest solution vertex, or smallest solution vertex is equal to 10,005. And so that's the case if that value hasn't been touched yet. And so if that's all true, then we can say that the smallest solution vertex is equal to vertex time 1. And we'll also need to set the collision point equal to the vertex that we just checked, which is the triangle P1E. And then we'll also want to run this check again for the vertex time 2. So just switch all these values. So if vertex time 2 is less than vertex time 1, and vertex time 2 is less than or equal to T1, and vertex time 2 is greater than or equal to T0, and vertex time 2 is less than the smallest solution vertex, then we can set the smallest solution vertex to vertex time 2. And now what we're going to do is just copy from ellipsoid vertex distance equals 2 all the way down to the end of that inside of the determinant if block. We're going to copy and paste that, and this section we will run for the second vertex, triangle P2E. So you need to change all of the places where it says P1E to P2E. And we are going to, of course, do that again for the third vertex. So get rid of those redeclaration of that float, change that to P3E, P3E, triangle P3E. And once again in the else if statement. All right, looks good. So now if the smallest solution vertex is not equal to 10,005, so it has been modified, the float vertex distance is equal to the smallest solution vertex multiplied by the velocity E.length. And the collision packet vertex is equal to a new collision packet, so we're going to use that constructor, and we'll feed into it the collision point, which is the vertex and also the vertex distance. And we'll feed it in an integer type 2. But we don't want to return that yet because we still have to check for our edges to see if there is an edge solution that is actually closer than the vertex solution. So now we'll consider the edge going from P1 to P2. So first we have to check if there's any time where the sphere collides against the infinite line that's going through this edge. And this happens again when the distance between the sphere and the line is 1. And we can once again reduce this to a quadratic equation with a equal to the magnitude of the edge squared multiplied by the negative magnitude of the velocity squared plus the dot product of the edge and the velocity squared. B is equal to the magnitude of the edge squared multiplied by 2 times the velocity dot product base to vertex minus 2 times the edge dot velocity, edge dot base to vertex, and C is equal to the magnitude of the edge squared multiplied by 1 minus the magnitude of the base to vertex squared plus the edge dot product with the base to vertex squared. And if this quadratic equation has a smallest solution, then we know that the sphere will intersect with the line at some point, but we don't know if that's actually within the edge's region. So we parameterize the line by a function f such that L of 0 is equal to the original point, P1, and L of 1 is equal to the secondary point on the edge, P2. And we can calculate the point f of 0 on the line where the intersection takes place. And if this is within 0 and 1, then we can calculate our intersection point and intersection distance. All right, so let's jump back into it. We're going to have a similar architecture for our edge section as we did for the vertices section. So we'll need a new vector 3f for the edge. We'll need a vector 3f for the base to vertex. So that's the ellipsoid position to the point that is the base of the edge that we are going to construct. We'll need a vector for the edge intersection point. So that's where the sphere will actually intersect with the edge. We need a float for the intersection distance. We need a vector 3f for the from edge point. We need a vector 3f for the smallest edge. We need a float value for edge time 1. We need a float value for edge time 2. We need a float for the smallest solution edge, and we'll set that to 10,005 once again. We'll need a float for the smaller solution edge, so that's for the edge time 1 or edge time 2. We need a smaller f, so that's that f0 I was talking about before, and we need a float for the smallest f, so the smallest f0, because we'll have multiple solutions, of course, because we need to check every single edge. So we'll say edge is equal to vector 3f subtraction between the triangle P2e and P1e. So this is the edge going from P1 to P2, and we'll store that in edge. And we'll say that base to vertex is equal to vector 3f subtraction the triangle P1e minus the ellipsoid position IE, and the destination is the base to vertex. So now we can start defining these values, and I'm not going to say everything here, but yeah, I'm just getting these values from the previous screen. And if you want more information about how these values are being derived, I will put a link in the description of this video for all of the math that we are doing. So I'm just going to speed this up a bit here. All right, so now if the determinant b squared minus 4ac is greater than or equal to 0, then we know that we have at least one real solution. So we can check to see if that solution is within the actual edge segment's length and space between the 2 points rather than just the infinite line. So we'll say that edge time 1 is equal to, once again, the messed up quadratic formula that I was using, and I will fix this at the end. It should be negative b plus the square root of b squared minus 4ac divided by 2a. And I'll speed this part up again. Alright, so now that we have our edge times, if the edge time 1 is less than or equal to edge time 2, so now we're essentially just comparing them to see which is the smaller, because we only want the first collision, as there will be a collision with the front of the line and the back of the line once again. So if that edge time 1 is less than edge time 2, we'll say that the smaller of the two solutions, smaller solution edge, is the edge time 1, else we'll say the smaller solution edge is edge time 2. Alright, but we still don't know if those are within the actual edge segment. But first, we need to check if the smaller solution edge is greater than or equal to 0 and less than or equal to 1. Because that is the time of the collision, and we only want those times between 0 and 1. So then we can calculate the f0 value. So smaller f is equal to the dot product of the edge and the velocity multiplied by the smaller solution edge minus the vector 3f dot product between the edge and the base to vertex. All right. So now we can see if this smaller f is between 0 and 1. So if smaller solution, no, just smaller f is greater than or equal to 0, and smaller f is less than or equal to 1, and also if the smaller solution edge is less than the smallest solution edge. So the first check is to see if it's within the time 0 and 1, and the second check between the edges is to see if that is the smallest time, because we only want the first collision, of course. And so if both of those hold true, I'm just got to get these parentheses correct. All right. So both of these hold true, then we can say that the smallest f is equal to the smaller f. All right, and then we have to initialize this smaller f. But first we'll say that the smallest solution edge is equal to the smaller solution edge. And we need both of these variables to calculate both of the collision position and the distance. So we will initialize the smaller f to -1. And now we can say that the from edge point is equal to our triangle P1E, and that the smallest edge is equal to edge. And then we can do the exact same thing as we did before and copy that chunk and paste it back in. Although you'll actually want to also reinitialize the smaller f variable to -1, because if that passed on the first edge segment, then it's going to be changed, unfortunately, and I didn't catch that in here. So make sure you also change up your triangle points that construct the edges here in all of the places. All right, so now we're going to do that again and make sure you change up these triangle values. We need to construct an edge between all of the points. So this one starts at P3 and goes to P1. Okay, and now that we finally have all of these, we have our smallest solution. And so if the smallest solution edge is not 10,005, so it has been modified, then we can say that the edge intersection point is equal to the vector 3f addition of the from edge point and the edge scaled by the smallest f. We had to cast that to a vector 3f, and we will store that in the edge intersection point. So we'll also initialize smallest f, but that won't matter anyhow because smallest f will have been modified if we have passed through this smallest solution edge is not equal to 10,005. So the intersection distance is equal to the smallest solution edge multiplied by the velocity length. And then we can construct a collision packet edge, and so that's a new collision packet, and we can feed that in for the position, the edge intersection point, and the collision distance is the intersection distance. All right, and we'll give it a type 3, and that is our collision packet edge done. So now we have a collision packet for the surface, the vertex, or the edge. And if it's been a surface collision packet, then we actually already returned from this program early. So now we have to just find out which collision packet is actually closest to our position in the world. And then once we have that figured out, we can send it off and return from the method. So we'll say that if collision packet edge is not null, or collision packet vertex is not null. So one of them actually exists and got created. Then we can try an if statement. If collision packet edge dot get collision distance is less than collision packet vertex dot get collision distance, then we can return the collision packet edge. And we'll try to catch that with a null pointer exception E. All right, and we're going to do that same exact thing essentially. We're just going to see if the packet exists, and we're going to surround it with the try catch and see if the vertex is less than the edge distance, and we'll return that as well. We'll return the collision packet vertex if that's true. And then if that doesn't go through, we also need to try to just return the collision packet edge. And if this collision packet edge doesn't go through and it was null, then we need to return the collision packet vertex, and that covers all of our bases there. If nothing went through, we detected no collisions, so we'll return null. And we should be done now, except I made a few mistakes. So we need to initialize this 2E space matrix to a matrix 3F. We need to, and that's because we called that .moo method on it. And then also that try catch statement with the legal argument exception didn't work out. So I've added in another if statement up there, and that will catch the object moving parallel to the plane, that undefined denominator case of 0 that we talked about previously. And that should be pretty obvious what that's doing there. So if the denominator is 0, we'll set t0 equal to 0 and t1 equal to 1. And then we still have that check to see if it's embedded in the plane. In this section here, we need to change the velocity E multiplied by t0 and actually explicitly multiply that out instead of using the dot scale function, because that was causing some errors. It was returning just a 0, 0, 0 vector for some reason. And also, of course, we need to change this determinant here, so it should be b squared minus 4ac is greater than 0, and we'll have to do that for all of these. But hopefully you caught that already. So make sure those are all correct. And then also we have to change the formula we were using for our time. So it's negative b, and inside the square root it's b squared minus 4ac. Make sure you get all your terms grouped correctly, and then we'll do that for all of the times, both the vertex times and the edge times. There were also some problems returning these collision packets down here. So if we surround that try statement with an if collision packet edge does not equal null, and if collision packet vertex does not equal null, that will work out a lot better for us. And then also we have to go back up here into the edge calculations, and the calculation for the A was wrong, and that just needs to be the dot product of the edge and the velocity E. And the smaller f calculation needs to be the division of that original function by the edge length squared. So we need to go through and do that for all of the A terms and all of the edge.lengths, or all of the smaller f terms rather. So A, we need the vector 3f dot edge there. So that's all correct. And we need to divide that b term by the edge.lengthSquared. And then we'll check the bottom one. So edge intersection point, we just turn that into edge. And the b term divide by edge.lengthSquared. And now finally, we have our collision detector complete. So we can go up, and I've made a little test folder here and constructed a bunch of collision detectors, with different vertices. And hopefully you can pause the video and see where all of those are and see the types of collisions. Of course, the first one is the position, the second vector is the velocity, the third is the triangle P1, the fourth is triangle P2, the fifth is triangle P3, and then we have our ellipsoid maximas. And you can see that we are detecting all types of collision. So I'm just adjusting the ellipsoid maximas here and rerunning it to show that we can collide at distances other than 1. So yeah, thanks to all of you that made it to the end. I hope that you all learned something that you can take away with you from this video and implement it in your own projects. So if you do end up using this system, please let me know, either through Twitter or through my email, which I'll put in the description below. And I will be working on a broad phase system as well as a collision response system in the upcoming weeks. So if you're interested in that, subscribe to the channel so you're notified when it goes live. And once again, thank you and have a pleasant day and happy development.